Right, nice to meet you all. Thank you very much for the invite. Very happy to be here. So, today I'll be talking about Eye2Gene. Um, there was supposed to be a really cool animation for the logo. But yes, so essentially we work with retinal scans and specifically on inherited retinal scans, genetic eye diseases. So they are a leading cause of blindness in, 30 plus, so the working age population. And they cause eye issues in very different, very distinct ways. So, for example, some of them affect central vision, some of them affect the peripheral vision. And the issue is, all of these diseases eventually lead to, you know, com- complete sight loss. So there's 300 genes associated with these. You know, individually, they can be quite rare. Um, so essentially, in a more machine learning hat, essentially 300 classes, class imbalance, some of them super rare. And, the first step in diagnosing these, identifying the right pathway is the genetic diagnosis. And that is essentially where we find out what part of the genome is causing that mutation, is causing the disease. So finding that disease causal gene. And the great thing is, there's roughly 300 plus clinical trials actively happening that, what basically save the sight. And, there's one already approved. And, that's absolutely great. These patients, some of them, super young, are, faced with this, ultimate blindness throughout for their entire life. These are literally showing them real hope. However, the issue with these trials and these therapies is super important that we identify these patients very early on. However, identifying these patients is extremely challenging. So in the UK, where genetic sequencing is quite fairly widespread, quite commonplace, it still takes over 5 years for a patient to find a genetic diagnosis. And even when we do the genetic sequencing, because of the amount of data that we receive, even in those 5 years, for a vast majority of those patients, roughly half of them, we still do not get the answer. We don't know what part of the gene, what is the disease-causing gene. And what this means, there's over 4 million patients worldwide without a genetic diagnosis. And because this is a lifelong condition, it represents a very significant health economic cost. So, in quality adjusted life years. And that's roughly, £500 million to the national health. And, the reasons behind this is, many, but there's very limited access to genetic testing sequences. It's very difficult to process that data. They're very scarce, very slow, overwhelmed. In the NHS, it takes roughly, a year, give or take, for, getting a reply from Genomics England. And it's super expensive. If you want to get this done in an accredited way, it can cost more than $1,500 for, a test. And what's more, worldwide, this is only available in certain countries. We're only looking at the tip of the iceberg there. The vast majority of the world, it's not, you can't get genetic sequencing at all. So for these patients, it's, very difficult, or if not impossible, to access, get to a diagnosis. So the way we are approaching it is a completely different way. Well, we asked a question, so instead of going down the way of genetic sequencing, getting a blood drop, sending it off, waiting 5 years, or however long, to get that diagnosis, is there a better way? And there is. This is a machine, an OCT machine that's available, in the UK in most, high streets, in opticians. So it's very cheap, very easy to get a very good image of the back of the eye. And that's a 3D image. So with Eye2Gene, what we are doing is taking 3 multiple types of those images, and we produce a report. We are saying what is the gene that's causing that disease. And we can do this is because each of these diseases, each of these genes, have a different phenotype in the retinal scan. And under the hood, just a very quick overview, we have essentially an ensemble of ensembles. So for each of the different modalities, image modalities, we have a separate ensemble modeling, and they all produce a list of multiple, predictions for each gene. And then that is all combined. If there are multiple scans for the same patient, that information is all combined, multiple visits, etc. That can all be combined to produce a final result. So when we look at genetic eye disease detection accuracy, we're at 93%, and for the top 5 gene accuracy, 86%. So, if we look at random, that is 1/63, so 63 class model. We have published this. So, do have a look at it if you are interested. And the reason we are able to do this is because we are very lucky to be based at UCL at Moorfields Eye Hospital, where we have this amazing data set. 60,000 60,000 images from over 4,000 patients with a genetic diagnosis, with the ground truth labels. And we're sorry, I've got autoplay on the images, so sorry. But there's 63 genes that we are dealing with there. And one thing you can see straight away, super obvious, some of those classes are more common than others. And that's, make things hard. One way we try to deal with this is with synthetic data. But when we looked into that, we showed that it didn't really solve the problem. The only real way of kind of solving that is by actually getting real data in from as much as possible. And the other thing is, if we look at the ethnic distribution of IRD patients in Moorfields, as you can probably guess, the blue on the right is white British. And there's some other ethnicities that are very, very small there. So, the data itself means that, if we want to build a truly, equitable, model, it becomes very, very difficult. And because these are inherited diseases, there's also ethnicity distributions by gene. So for each of the different classes, they have different incidence levels in different ethnic groups. So I know there's multiple versions of oranges there, but this, I don't know if it's showing. Nope. Yeah, there. So this orange is South Asian. And as you can see, there are multiple versions here, multiple genes here that have higher, distribution in certain countries. So if we want to truly, get a very well-rounded data set, we do have to work with international collaborators. It can't just be done, even though London is a very multicultural, center, it's amazing, but to truly, represent, the distribution of the data that we are seeing, we need to look further beyond. And as I said before, each of these classes can be quite rare internationally. So the only way to build that, highly accurate, highly equitable model covering all these gene classes is for us to pool all of our data, internationally. So for the medical community to come together, and work together essentially. And we have been quite lucky. So since we published in Nature Machine Intelligence, we've received amazing feedback from the community. And there's been a lot of, very positive, very highly interested clinicians. We've had interest from 85 plus sites from across 36 countries. So I'm not sure if any of you, I know someone did mention a data access agreement or, collaboration agreement. It takes a very long time to do that. And if we had to do that in 85, with 85 times in 36 countries, and to make things even more fun, data governance laws are not the same everywhere. They're very different. Some places do not even allow you to take any data out. How do you deal with that? And, this is just general data. That's already very difficult. When you start talking about medical data, that becomes, near impossible. So, relying on accessing data directly, I don't think it's not sustainable. It's not really possible, perhaps. And I think the only way to get around that is federated learning, to truly produce a model that is fair for all, that is truly highly accurate across all of the different gene classes, and also works well. So we were very lucky to work very closely with Javier and others from the Flower team, and we got into this accelerator program at UCL. So they have a CDI accelerator program. And essentially with that, we got very close support from Amazon Web Services. So I'm not sure if anyone has worked with hospitals. If you try to, install a GPU node inside their network, not going to happen. So that's exactly what we found out. And, the best way to get around that is to move things to the cloud. Still very difficult, but somewhat less so. And also, it makes it a lot more scalable. So yeah, loads of challenges, loads of fun. Clinicians, they're super interested, but very limited technical expertise. So they bring in the IT, and they're not very happy with running, code that they're not familiar with on hospital systems. And, like I said, it's difficult to get, those compute inside each of those hospitals. So what we wanted, very wish list, if you may, something very technically simple, easy to set up, minimally reliant on hospital IT resources, and separate entirely the compute elements and the communication and the data. So like I said, we were very lucky to have people from AWS really help us with this. And I was actually having a discussion with someone earlier today where, one thing that we did which was slightly different was we used the internal AWS network for communication. So we used something called VPC pairing. So when we're talking between sites, even though the main head node is in London and one of the client nodes in this Australia, Germany, wherever, all of that network, all of that talk is happening internally within AWS network. So nothing is getting exposed externally. Everything is being, set up in a very careful way. We're using private subnets, so we had to do a lot of thinking. And we're very lucky to have the expertise support from Flower and AWS for that. And, another thing is cost. AWS is great, but yeah, we need to be careful of costs. And obviously, then who pays for that as well? So if it's us, we have to make sure it's really efficient. So in terms of the kind of legal side, to kind of keep everyone happy, each hospital owns the account for their site. The actual client node sits on a very tiny machine, so it costs next to nothing. But then the actual tiny machine, if you try to run any training on it, it will take a millennia or two. So you basically want to farm that work out to a GPU node. So that's essentially what we did. So we kind of basically built something that triggers out train jobs and set up a system using Amazon Batch, AWS Batch, to kind of set that entirely up. And the way we configured it was using something called spot instances. So if you don't know what spot instances are, essentially they are machines that AWS kind of gives them away at 90% discount. But the thing is, essentially is AWS have loads of spare compute. If nobody's using it, you might as well just give it out for next to nothing, but then you can take it back very, very quickly. So we used that, so we got all of that very efficient, very cheap, and kind of ran that. So another way of showing it, essentially, we used Nextflow, which was used a lot more in genomics, but we used it for where we literally had a single process running our GPU train job, And the reason we use Nextflow is that it, integrates very easily with AWS Batch. So yeah, so basically this is what we built. And in our pilot, again, healthcare, a lot of resistance, lots of fun. So what we did, we worked with partners where we already had a data access agreement in place. So even if there was a data leakage, whatever, it was less of a concern to them because we already had permission to go there and set things up. So in this pilot, we worked with very, some partners in Germany, another site in the UK, and Australia. And basically, we showed we were able to get everything working. And with that federated kind of side of things, we were basically hoping to see that increase in accuracy. And the thing is, we're hoping to see this more as we get more and more people to join this network. So in terms of where we are right now, we kind of felt that, yes, it's great. Everything works very, very well. However, if you can make it, very easy to use is extremely important for clinicians. So building an end-to-end GUI, a Windows application, and it has to be Windows because, NHS loves Windows for some reason. Yeah, and so that will basically control everything. So it's a single click to kind of set up your AWS account, set up all the infrastructure necessary. So we use infrastructure as code, so using CDK essentially, to set everything up automatically. And then on top of that, there was another massive problem. Hospitals have loads of data on massive file stores. How do we get that data into the cloud in a kind of regulated way? But also, hospitals have, as we know, not great network connections. So basically setting it up so that you don't just use all the bandwidth, you don't want to be during a busy clinic and then nothing works, which wouldn't be fun. So you set this up so it automatically has that queue on a way where the clinician feels in control. They are in control. They see what data is being sent up. And we build this in a way that automatically crawls these file stores directly at the lower level. So the partners we're working with initially are, they stored the underlying database using DICOM. So that's a standard, so that's great for us. Not all of these sites, not all of these providers do, unfortunately. But, we're starting with the DICOM viewer, so we crawl these massive databases, and then allow the clinicians to select which patients they want to upload, and then add the associated labels with that. So creating the CSV that we use as data scientists all happens automatically. So if you try to ask a clinician to create a CSV, this has to be in this column, and so on, not going to work. And there'll be spaces everywhere, and loads of fun. So all of that has to happen behind the hood, essentially. And then it needs to have very strong audit logs. And this is extremely important. A clinician, each site needs to feel in complete control of what's happening of their data, and that's extremely important. And one thing we've already started doing is our AI software, as inference, is already integrated with some of the scanning devices directly. So what we're trying to look into is to see if we can integrate that directly into our federated platform so that the clinician doesn't need a separate GUI. Because installing the GUI on somebody's hospital is going to be a lot of fun. So if you can get around that by integrating that directly into software that's already in the hospitals, allowing clinicians to directly log into their system that's already there, drag and drop into the Eye2Gene federated network, and then basically go from there. So that's what we're looking into. And also, we want to be a bit more integrated with the Flower AI community, see what we can provide back, see if we can open source some of our stuff, which is largely open sourced, but see if we can, tell our story essentially and, provide more back. And then also, finally, actually get it running in production and, reach out to all these super interested clinicians, get them on board, and build something that can actually make a real difference. So yeah, acknowledgements. It's a lot of clinicians, a lot of patients. That are that need to be thanked for this work. And yeah, well, thank you very much for the Flower team as well for supporting us with this. And yeah, we're trying to make Eye2Gene a genetic diagnosis in a blink of an eye. Cool, thank you very much.
I think that was maybe the best talk so far today.
Thank
I think it was really good. So do we have any question? Yes.
Hi, thanks for your talk. I was curious about the design with the spotted machines and how do you do to, like, if during training the machine is pulled out, are you checkpointing after every epoch, or how that works?
So you mean the spot instances, essentially? Yeah. So the issue with spot instances, I didn't tell you the downsides of it. So it's 90% cheaper, which is amazing. But the AWS, if they ever need it back, they give you 2 minutes notice, which is not great, and they don't give you a chance to pay more or whatever. It's gone. So what you can do is do exactly what you're saying. You basically have a, I think PyTorch, a number of them have a argument where you can actually basically store your checkpoints and then restore it. There's also other ways of kind of dealing with it so that it automatically continues from where you left off. Yeah, so it's basically, we have something we've been exploring. So at the moment, the way it's currently done, so we're storing all the checkpoints, but we're not continuing from the last run. So it's something we obviously want to kind of optimize. The nice thing, one of the reasons why we're using Nextflow is that it automatically recognizes when a job has failed because of some issue. So if AWS says, oh, we want our server back, it will automatically rerun that job. One thing we're quite lucky about, the current training job, given that we're using spot instances, is costing us 17 cents or so for the actual training job. So it's not really breaking the bank. So we're good for now. So it's not as a priority, but it's something we definitely would look into if we go for something a bit more complex.
And I assume you have like a central service that needs to be running all the time. So that's kind of like a permanent machine that then orchestrate the spotted instance.
Absolutely. So basically, if I go back to somewhere, this thing. So these head nodes, it's I actually put the instance class. Probably nobody, yeah. But essentially, they're not super massive. They're not super small. They don't have a GPU, so they don't cost much. But in total, one of them might cost, I don't know, $30 a month. If you pay up front for, 3 years, I'll bring it down to $10 a month. So it's not, again, not crazy money, which is why you can have those main, servers running all the time. And, then only trigger the jobs as and when needed.
Sorry, another question. But in the same slide, are for regulation purpose, the trusts are uploading their data into AWS. Is that considered inside of the same trust? How you convince them that that's safe or like compliant?
Absolutely, very good question. And it's always a lot of fun convincing IT people that everything is fine. But in reality, most of their stuff is already on AWS. So NHS login, for example, the key to the Palace essentially is run by AWS. I think it's Cognito service. So a lot of NHS is already using AWS. They're already using the cloud. So as long as you're providing your infrastructure in a very secure way, that's fine. And we were very lucky to work very closely with AWS. they reviewed our CDK templates. And on top of this, we have ISO 27001. And it's all of these additional backing that is extremely important when you make the case. But again, it's not fun.
Thank you.
I really liked your accuracy curves that that you were showing for different countries. I was wondering, do you see any trend where some particular countries don't benefit from federated learning, or why do you get this gain? Are there particular classes or particular particular categories where they're benefiting from, or what does your test set look like when you are doing that ultimate federated learning based?
100%. So our test set is based on data from our more fields. So we have a test set there, but then we also have an external test set from multiple different countries, including Japan, Brazil, a few different sites in the UK, and basically it's about building, using that essentially diverse data set as the test set. And coming back to your first question about why is it that different countries, some countries may benefit a lot more compared to others, and it's all about how much data are they providing that is distinctively different to our data. So it's about the whole real benefit of federated learning is about making your data set much more diverse, catching those edge cases, getting more representation of those classes that are not as well covered in your training data set. So if there is a country where because of there might be a much higher incidence of a certain gene class in that country, if we can bring that into our data set, train on that, learn on that, obviously the accuracy for that gene class would really improve. And they would benefit because they see many more patients from that background.
Do you ever see the other way around, where the accuracy decreases with respect to the local client training? Because I am trying to work on datasets from 8 different countries, and I'm seeing when I'm doing federated learning, some countries do benefit, where some others don't really. The accuracy goes down, probably because of the class distribution.
Yeah.
But I wanted to ask if you have seen anything like that. Or
we haven't yet, but it's something that we're quite early in our when we're looking at this, and we are looking to onboard a lot more hospitals and different countries, and we're definitely looking into what's the best way of providing the service. We at the moment we have a multiple class AI model for this task. Perhaps the answer is to build a separate model for every single class, and maintaining that, which may be fun, but it's going to be basically looking at that problem and seeing what we can do based on what we see.
Thank you so much.
Thank you so much. That was beautiful. And if you're staying around, I would just love to talk to you a little
Absolutely.
bit more on the technical side. I'm involved with the East of England Secure Data Environment and based at COH. But my question actually is more on adoptability, because obviously at the moment you have your champion clinicians, which of course you need, but that is going to not provide equitable care for patients in the longer term. So what's your kind of target operating model? How do you see this potentially being adopted? And then secondly, how crucial is that you are able to pinpoint the exact gene in terms of not necessitating genetic confirmatory, say, test after you've done this test?
So it's, we've actually been working very closely with the MHRA. So this is actually a picture at the MHRA, I think a few weeks ago, or 2 weeks ago, where basically we're working with them as part of the AI airlock, which is a pilot study where they are trying to get, some AI companies involved to see how the regulations, change for real AI and how to get that into front of patients. And it's not very easy. It's a long-winded process, and everything comes down to your intended purpose, your intended use, as they call it. And there are multiple different ways where Eye2Gene can be used. And also, we've had massive discussions and about when we show our report to the clinicians, what do we show them? Do we show them a lot of information? Tell them what part of the image is actually providing this information? Or, do we just tell them the answer and that's it? And also, like you quite correctly said, do we also then have to go on and do the genetic confirmation? And I think it all comes down to the regulations and what we kind of put down as intended use. And our initial goal is to kind of basically get class 2, approval, get CE marking as a companion diagnostic. So basically, we would have a service where we would basically be able to provide an answer straight away, and not have the patient not let the patient wait for 5 years, where they essentially have no idea what's going on. And the benefits of having a much more timely benefit is knowing what's going on is very useful for the patient in terms of family planning. There's multiple benefits to the patient. So we would be able to tell the patient straight away, so the doctor would be able to, that this is potential, and then from there they would then be able to we would actually be able to actually go in and sequence the 5 genes instead of the entire genome. And then in terms of the variant prioritization, we also have a product where basically we use the phenotypic data. So if there's anyone from a genetics background, so there's tools like Exomizer, these are tools that basically help, with genomic data, you get loads of changes, variants. Identifying the right variant, the right change, is extremely difficult. So when we provide this imaging data, the AI with that, we kind of optimize that as well. So basically providing this full-end service is what we're trying to do. And I think given where we are right now, so we're just at the stage of spinning out, I know for a fact, over the last, 6 years or whatever, our intended use case has changed quite a bit based on feedback. And I think it will change when we hear back from the MHRA, when we hear back from, clinicians. It's all about, working together, collaboratively to see what is the best way and the fastest way to get this in front of patients.